So last class we learned about valence electrons, core electrons. And one of the reasons that we learned about those valence electrons, it gives us an explanation of what the charges are going to be on our elements on the periodic table, the ones that have the same charge every single time. And the other reason is that it gets us a good intro into bonding theories. Up until now, we've only looked at coming up with structures for, not really structures, but we've worked with ionic compounds and like what the ratio of the different cations, the positively charged, and the anions, the negatively charged, what those ratios are going to be like for those formula units. We haven't really looked at molecules. So bonding theories with valence electrons, we can start to work on coming up with combinations of compounds with nonmetals. So we're going to be able to do some fun stuff like predict the formulas of compounds. This works especially well for ionic compounds, even though we already have tools to do that. And we'll also be able to do shapes. So we'll be able to draw shapes of molecules. And that's going to inform us about some other properties that occur that are related to molecules and who likes electrons more. The bonding theory that we're going to cover for this class is very simple. You don't need a supercomputer to do it. And that's part of the reason that we're doing it. It's Lewis theory. This is our simplest method. If you can believe it, this is the simplest it gets. And it's basically like we're learning a fun little game. And I say fun because I think it's fun. It might not be fun for you, but once you learn how to play the game, it is kind of fun and satisfying to get the correct answer, I think. So let's get into it. So in Lewis theory, our valence electrons are represented as dots surrounding the symbol of the element. So for example, if we have sodium, sodium on our periodic table is in group 1. So that far left column, it's going to have one valence electron. So we would represent sodium as the symbol for sodium, Na, with one dot on it. And this is our Lewis structure. So this is the Lewis structure for sodium. And as a reminder, the number of valence electrons for any of our main group elements, anything in our S block, the left 2 columns, and our P block, the far right 6 columns, is equal to the group number or the last number. So like for 13, 14, 15, 3A, 4A, 5A, so you'll sometimes see them, or 3, 4, or 5. So that's like our shortcut, or a shortcut for coming up with the number of valence electrons. You can always do an electron configuration and come up with it that way too. So let's do an electron configuration for oxygen to get its number of valence electrons. Let's say that we wanted to do it the long way. We find oxygen on our periodic table. It's in period 2, group 16 or 6A. So oxygen has 8 protons. I was thinking of carbon. 8 protons, that means it also has 8 electrons. So we need to do our electron configuration with 8 electrons. Our lowest energy number and letter combination is what? 1s. So we've got our 1s. Our s subshell has one orbital. It's just the sphere shape. Since we just have one shape, each shape holds 2 electrons, so 1s2. Up next after 1s is 2s. 2s, since it's an s, also only holds 2 electrons. And then after 2s, if we're reading off our periodic table especially, from 2s, we move across to the p block, still in row 2, so we're in 2p. and we can place our last 4 electrons there. So that would be our electron configuration for oxygen. And we have how many valence electrons? We've got 2 sets that have the number 2 in front of them, right? 2s2, 2p4. 2 plus 4, we've got 6 valence electrons. Alternatively, the shortcut looking at oxygen where it is, 16, 6a, it has 6 valence electrons. So our Lewis structure for oxygen, what's the symbol for oxygen? O. And we have 6 valence electrons, so we're going to put 6 dots around it. It does not matter where the dots go. Position of the dots is not important, as long as if is faster, they are spread out. So let me show you a different way that we could draw that Lewis structure, Lewis dot structure. All right, so we could put our pairs down or to the right. We could have pairs left and right. What we wouldn't want to do, so these are both good. What you don't want to do, though, is do 3 pairs. So we want to spread our electrons out rather than clumping them up in pairs. So I'll usually draw them in singly first, and then we pair them up after. So each of those dots represents one of our valence electrons. Location's not that important, but fill in the dot singly first, and then pair them. If we have atoms with 8 valence electrons, those are especially stable. 8 valence electrons is that noble gas electron configuration that we were looking at last class. And when we're doing Lewis dot structures, 8 dots is an octet. The oct being 8, just like October is the 8th month of the year, or it used to be. And then the et, like duet, quartet, etc., right? So like a group of 8 is our octet. Oct like octopus. We can do our Lewis structures for the first 10 elements. So for hydrogen, we've got 1 valence electron. How many valence electrons does helium have? How many electrons does helium have? 2. So helium's a bit of a weird one. Helium only has 2 electrons. It can't have any more than 2 electrons because we just have the 1s, and so helium is actually going to pair right away. And then when we move on to lithium, lithium is in period 2, so we're starting over, new shell. So lithium has 1 dot. Beryllium, we're adding 1 more dot because we've got now 2 electrons in our valence shell, our n equals 2 shell. So we've got 2 dots. Boron, we get up to 3. Carbon has 1 more. Hopefully you're seeing the pattern. Nitrogen, we've got 5 valence electrons. We saw oxygen earlier. it has 6. Fluorine has 7. So we draw 7 dots around it. And then neon is our completely full octet. So we're just filling in the number of electrons, the number of dots for however many valence electrons we have. Questions about how we're doing any of that? Again, helium here is stable with a duet of 2 electrons because the n equals 1 only has the s subshell. 1s holds up to 2 electrons. We don't have the p subshell to fill in to get up to 8. That's why we only get 2 electrons. All right, so that's our starting point, our very most basic little bit for Lewis theory. In Lewis theory, we've got 2 types of bonds. We've seen one of these types of bonds before. Our bonds are either sharing or the transfer of electrons. We've looked at the ones that are a transfer of electrons. Those are ionic bonds. So ionic bonds involve a transfer of electrons. Ionic bonds form in ionic compounds, meaning that we've got a metal, typically, and a nonmetal. Like our favorite salt, table salt, NaCl. Sodium's a metal, chlorine's a nonmetal. Those sort of bonds involve a transfer of electrons. In covalent bonds, the co, like cooperative, working together, and valent being the outside, so they're sharing their outside electrons. And this is going to be in molecules. So molecules have covalent bonds. So things like methane, CH4, that's linked together by sharing electrons rather than giving away or stealing electrons, however you want to think of it. We also have our octet rule. This is a big one. In all of our chemical bonding, be it ionic, a transfer of electrons, or covalent, sharing electrons, our atoms are going to obtain outer shells with 8 electrons. So 8 electrons is the goal. When an atom gets 8 electrons, either by sharing or by taking or by giving away electrons, then we consider it to be happy or stable, or it's not going to do anything else. The exception to that rule is little things like hydrogen, lithium, and beryllium. They have a duet rule because their closest noble gas is helium. Helium only has 2 electrons. because of that 1s thing that we talked about earlier. Usually how this plays in is hydrogen is happy with just 2 valence electrons. Otherwise, it's 8. Let's write out Lewis structures for aluminum and selenium. I'll do the one for aluminum. Finding aluminum on our periodic table, it shows up in group 13. The A or B designation for that would be 3A. So aluminum is in group 13/3A. So aluminum has 3 valence electrons. I'm going to shorten valence electrons as VE. So we've got our symbol for aluminum, and then we put 3 dots around it. The location isn't exactly critical as long as they're just by themselves, singly rather than paired. So that's our Lewis structure for aluminum. Now you do the Lewis structure for selenium. I'll give you a little bit of time to do that. All right, so that Lewis structure for selenium, Se, is in what group? What's the number of the group? 16 or 6A? So it has 6 valence electrons. So our symbol Se, and then we're going to add 6 electrons to the outside. We'll add them singly first, so we've got 4, and then we can pair them up. So that would be one correct Lewis structure for selenium. You can put the pairs in any of the 4 sides. So we'll talk about compounds first. They're arguably a little bit easier. So when our nonmetals and metals bond, metals bonded with a nonmetal is an ionic bond, an ionic compound. Electrons are transferred. The metal gives electrons to the nonmetal. Since the metal loses electrons, it becomes a cation. It now has a positive charge. It has fewer electrons than it has protons. The nonmetal picks up some extra electrons, so it gets extra negative charge, and so it becomes an anion, and it has a negative charge. And then because we've got positive charges and negative charges, those stick to each other like a magnet. And in Lewis theory, we're going to represent that by moving the electron dots, we'll use little arrows to show it, from the metal to the nonmetal. So let's say that we did that with the selenium and the aluminum. I think we might have that coming up on the next slide. So aluminum can give 2 of these electrons to selenium. After those get transferred over, we'll have 1 leftover valence electron on our aluminum, and our selenium will have a full octet. Just an example of what moving those electrons might look like. There's some other notation that we'll add to that. Okay, this is an easier one actually. We're doing Lewis structures for potassium and chlorine, and we want to show the electron transfer that happens when they bond. So sodium, potassium, K, on our periodic table is a group 1 metal. Since it's in group 1, it's going to have one valence electron. Chlorine is over in 17, or 7A. So chlorine has 7 valence electrons. I'm going to draw them in green. So those are our Lewis structures, and we can transfer this one electron from the potassium to the chlorine. This then becomes K+. And we'll have the chlorine with its one electron from potassium and the 7 that it started with. And to make it clear that these electrons belong only to chlorine, we put brackets. So the brackets show that these electrons are only on chlorine. They're not shared. That's the little bit of notation that we were missing on the previous slide. Questions so far? Okay. So we saw in that previous slide, chloride has an octet. It's got 8 valence electrons. Eight electrons on it. Potassium lost its only electron. And so it's now left, if we look at our periodic table, potassium has now the valence electron configuration of argon. So we peeled off that last layer, and secretly, it's got another full shell underneath. So empty can also be an octet. It's not always going to be an octet for hydrogen. For example, if it loses its one electron, it doesn't have any electrons, so it wouldn't have an octet. But things that are bigger than hydrogen, if we peel away that layer, the valence electrons, then we get to the previous noble gas. So that also works out nicely. And then this third bullet point just saying that if we've got something that's negatively charged, something that's got electrons on it, we write it within brackets, like we saw on the previous slide, and the charge goes in the upper right-hand corner. Just like we saw on the previous slide. This will be important on your Lewis structure worksheet. Okay, one for you to try. Write the Lewis structure of the compound NaBr. I'll give you a minute. All right, coming back, we've got the Lewis structure for sodium bromide, an ionic compound. We would want to start with our symbols for both of those elements. We were given them. And we would find from the periodic table sodium's group 1, it's going to have 1 valence electron. Bromine is in the same group, the halogens, as chlorine. It's going to have 7 valence electrons. Sodium is going to give away its 1 electron to the bromine. That'll give sodium an empty shell, which is the same as a full octet underneath. And then our bromine now has picked up that 1 extra electron. 1 electron means 1 negative charge. We put brackets around it and give it a negative up in the upper right corner outside the brackets. So that's our Lewis structure for sodium bromide. We can also do ionic compounds with things that aren't just going to form 1 positive or 1 negative charges. So for example, with calcium chloride, calcium is Ca, and it's an alkaline earth metal. It's in our group 2. It's going to have 2 valence electrons. So we'll draw those in. I'm going to draw them in on opposite sides. And we're also going to have chlorine atoms. We saw chlorine before. We know it has 7 valence electrons. In order for that chlorine to get, a valence shell, full valence shell, an octet, it can pick up 1 extra electron. So if we do that, we'll have calcium still with 1 electron and a positive charge. And then in brackets, we'll have our chloride anion. With its negative charge outside the brackets. In order for this to be a good Lewis structure, in order for us to have a good Lewis structure, everything needs to have a full octet. Do we have full octets for both of our atoms here? We do not. Which one is missing a full octet? Calcium. Calcium still has 1 electron. That's a problem. That is not a good Lewis structure. So I'm going to copy paste this, and we'll think about, okay, where could we get rid of that 1 electron that calcium has? Where did we get rid of our first one? We gave it to a chlorine. Good odds that there's probably another chlorine around. Let's just say that there is. So another chlorine pulls up. Same configuration as the previous one. Calcium can give its other electron away to that chlorine, and it becomes a chloride. So change a couple things around here just for color consistency. And we would end up with that as our Lewis structure. Now calcium's given away its outer shell, it's given away its valence shell, so it secretly has a full octet. And both of our chlorines are now chlorides. They've got their full octets thanks to the 1 electron that they each received from calcium. Questions about that? Most of our time isn't going to be spent on ionic compounds, partly because you can come up with that formula, CaCl2, just crisscrossing, right, with the charges. We can do a similar thing with magnesium and nitrogen. How many people want to try doing the magnesium-nitrogen one by yourself? How many people would rather I just do it? Okay, it looked like maybe people were a little split, so I'll give you a little bit of time to work on it, and then I'll race through it. All right, we're going to get rolling with our Lewis structure with magnesium and nitrogen. Starting off, we'll want one magnesium and one nitrogen. Magnesium is Mg. It lives in group 2, or 2A. It's got 2 valence electrons. Nitrogen, N, is group 15, or 5A, and so it's going to have 5 valence electrons. We can donate 2 electrons from our magnesium to our nitrogen. That's going to result in us having zero electrons on our magnesium. Nitrogen is 1 short of a full octet. So to help out the nitrogen, we can say another magnesium is going to roll up and donate 1 of its electrons to the nitrogen. However, we now have 1 electron left on our magnesium. We'll need to find a place to give that away, and nitrogen is a great place to give that away. So we add in another nitrogen, this one with, again, 5 valence electrons. Give away our 1 electron that we've got left. So now our magnesiums, right, these 2 magnesiums are both good, our nitrogen's good, but our other nitrogen is too short. Not the wrapper, it just needs 2 more electrons. Fortunately, we know that a magnesium comes equipped with 2 electrons. So if we add 1 more magnesium in, we can scooch those electrons over and now that nitrogen is good and our last magnesium is good. To fill out the nomenclature, we would add in a bunch of 2 pluses and 3 minuses with the brackets in purple there. So it would look something like that, a little bit of a mess. But what this predicts for us is that our formula, our ionic compound formula, is Mg3N2. Like I mentioned earlier, we can come up with the ionic compound formulas pretty easily, though. Right, magnesium's a 2+, nitrogen's a 3-. If we crisscross it, we get Mg3N2. So we're not going to spend very much time. This is like the last of ionic compound stuff that we'll do, probably. Questions about any of the steps for that? All right, on to the arguably more important stuff, covalent Lewis structures, where we're sharing electrons. When nonmetals bond with other nonmetals, we get molecular compounds. So nonmetal plus nonmetal equals molecular compound. We know that from our nomenclature. Or you may remember that we talked about that during nomenclature. Molecular compounds use covalent bonds instead of ionic bonds. So we're sharing electrons. And this is where Lewis theory is a little bit more helpful. So let's look at Lewis structures for hydrogen and oxygen. And then we'll show what water looks like based on that. So our Lewis structure for hydrogen, H, it's got 1 electron, so 1 valence electron. Oxygen, we saw earlier, is O, and it's got 6 valence electrons. We can share electrons between our hydrogen and our oxygen. Boop. So now our hydrogen and our oxygen are sharing these 2 electrons. What this means is that these 2 electrons count for the valence shell of the hydrogen. Hydrogen needs a duet. It needs 2 electrons. It's got 2 electrons. It also counts for the oxygen. So oxygen has now picked up 1 electron. So it has 7 electrons around it. 7's not a full octet. So we'll need to bring in another hydrogen with 1 electron. And we can scooch that in. And now we've got another set of shared electrons. So in this Lewis structure, each hydrogen has a duet, the hydrogen equivalent of an octet, and the oxygen has an octet. So they're all happy, little air quotes, because atoms don't have feelings, but we think of it as them being happy. They're stable. And that is the structure of water, H2O. We also have multiple types of pairs of electrons. So if we look again at that structure for H2O, we've got some shared electrons. The shared electrons, they're circled in orange. Go Tigers. That's a bonding pair. So that's a pair of electrons that's connecting those 2 atoms together, linking them together. We also have lone pairs. So lone pairs are only counted towards or counted for oxygen's octet. Those are not being shared. They only belong to oxygen. You can also call those a non-bonding pair. So this is one way that we can represent things within our Lewis theory. More frequently, though, rather than showing 2 dots between our electrons, we'll show our bonding pairs as a line. And I think that that's a much better way of looking at it. It's a little bit less confusing. It's fewer dots to look at, but you have to remember that each of those lines means 2 electrons. So each of those lines represents 2 electrons. And that's typically how you're going to see bonds shown for chemical formulas, structures. So that's how we'll be looking at them basically the rest of the class. Lewis theory also does something nice for us. It shows us why halogens, fluorine, chlorine, bromine, iodine, form diatomic molecules. So if we look at the Lewis structure for bromine, Br has how many valence electrons? Has 7. So we draw 7 dots around our bromine. You can draw them wherever you like. I'm drawing it this way strategically. Is bromine content to be by itself? No, it is not. It wants to buddy up. And what better way to do that than to buddy up with another bromine that also has 7 valence electrons? So these bromines can share 1 pair of electrons they'll have a line between them representing a bonding pair, and they'll have 3 lone pairs. So by bonding, each bromine atom gets a full octet. And that's more stable than not having a full octet and being by themselves. Lewis theory also predicts that hydrogen exists as diatomic molecules, because hydrogen is going to have 1 electron. And again, if they share those electrons, then they get a full duet. So we can represent it with 2 dots in between them, or with a line. So each atom, each hydrogen atom now has a full duet. It's got a noble gas configuration, so it's nice and stable. So the thing that we did for bromine also applies for chlorine, also applies for fluorine, also applies for iodine, because those are also halogens. We can also share more than 1 pair of electrons. So oxygen is a good example of this. Let's look at oxygen. Oxygen is a 6A, or group 16 element, and it's going to have 6 valence electrons. So if we've got 2 oxygen atoms, and they share one of these pairs, they form 1 bond, we'll have something that looks like this. Are those oxygen atoms happy? Do they have their full octet? They do not have their full octet, right? So they will form another bond, and that becomes oxygen double bonded. So we've got 2 lines now, 2 lines, each line equals 2 electrons. So we've got 4 electrons in the bonds, and each of our oxygens also has 2 lone pairs. So between the double bond and the lone pairs, we've got a full octet for each of our oxygens. Questions? We can also have triple bonds. But let's talk about double bonds a little before we get there. So a double bond is when 2 electron pairs, 4 electrons, are shared between 2 atoms. if we think of bonds like rubber bands, we're putting 2 rubber bands around something compared to 1 rubber band around something, right? 2 rubber bands is going to pull more than 1 pair of rubber bands. Our double bonds are shorter. They're pulling more. And they're also stronger than single bonds. So double bonds are shorter and stronger than single bonds. I think for most people, that makes sense. It's a pretty reasonable thing to think about. And that's a fact that you should know. You don't need to know the bond lengths. Some scientists measured bonds between things. It's 121 picometers, really small distance between atoms in a double bond. In a single bond, it's more like 148 picometers, also a really small distance, but a little bit longer. Okay, now on to triple bonds. Let's think about N2, nitrogen gas. So nitrogen is in group 15, or 5A. It's going to have five valence electrons. So what we can do with nitrogen is do 3 bonds. You'll find if you do only 1 or 2, you don't quite have enough valence electrons for either of your nitrogens, but 3 is just right. And this is a triple bond. A triple bond has 6 electrons. Each line is 2 electrons. 3 lines times 2 electrons is 6 electrons. We also have 1 lone pair, which is 2 electrons. So we have 8 electrons on each nitrogen. That's a full octet, so nitrogen's happy with that triple bond. So we've talked about why hydrogen forms a diatomic molecule, H2. We've now talked about nitrogen that we see here, also oxygen, and then we talked about our halogens, fluorine, chlorine, bromine, iodine. That's all of our horses need oats for clear brown eyes, or our Brinkelhoff elements. Right? All the ones that form, or that H7, however you want to think of it. All of those form diatomic molecules, and that's because of what we're seeing here with Lewis theory, so that they get full octets. So these are all diatomic to get full octets. That's why they exist that way. Triple bonds are when 3 pairs of electrons are shared between 2 atoms. Any guesses? Which is stronger, a triple bond or a double bond? A triple bond. A double bond was shorter than a single bond. Do we think that a triple bond is shorter or longer than a double bond? Triple bond is also shorter than a double bond, right? It just makes sense. So our triple bonds, 3 bonds, just like 2 brains. It's better than less, fewer. So 3 bonds is stronger than 2. No surprises there. And because it's stronger, it's also shorter. This also makes nitrogen relatively unreactive. There are circumstances where it will react. I think we've seen examples of chemical reactions involving N2 gas, but you have to have really high pressure and temperature in order for those triple bonds to break. And now the fun thing that you don't need to know for the class, but I like talking about, is N2 is often used instead of carbonating beverages, you can nitrogenate beverages. So like if you've had nitro cold brew, so it's used to make things like nitro cold brew. And because of the way that nitrogen behaves, it forms different sized, smaller bubbles than CO2. And also because it's unreactive, it doesn't mess with the thing that you put it into. It doesn't affect the pH. So you can add it to coffee and it still tastes good. You can also use it to like displace other gases. So you can pump into, like sometimes you'll buy like Keurig cup pods that have nitrogen pumped into them, or like little foil wrapped coffee things. Nitro is also in Guinness, famously. And it makes for that smooth flavor. Also, I think you can get Pepsi with nitro in it, so that's fun too. All right, that's all set up for writing out more Lewis structures. So when we are writing out Lewis structures, we want to first set up a correct skeletal structure for the molecule. We'll be given a formula. So we want to just kind of lay out the skeletal bits, the bones, the bare bones of the molecule. Where are the atoms? Just relative to each other. Our hydrogen atoms are always going to be terminal or end atoms, because hydrogen can only form one bond. So hydrogen's always going to be on the outside, and we will try to be symmetrical when possible. Nature likes symmetry. It's more stable. We'll see examples of things being symmetrical. Let's say we wanted to do a Lewis structure for CH4. That's something that's nice and easy. To make it nice and symmetrical, we would have our carbon in the middle, and we would surround it on all sides with those hydrogens. So we can see a line of symmetry left and right. We can see a line of symmetry top and bottom, right? Mirrors of each other, nice and symmetrical. And our hydrogens are all in terminal positions. Then what we would do, now that we've got this basic structure, we need to figure out how many valence electrons we have to put on the board. So we're going to sum up our valence electrons for each of these. We have one carbon. Carbon has 4 valence electrons. We've got 4 hydrogens with 1 valence electron each. So we've got 4 valence electrons coming from our carbon, and we've got 4 valence electrons coming from our hydrogens, for a total of 8 valence electrons. There's also cases where we'll have ions, and we'll need to adjust our charge when we're doing those. So like NH4 plus ammonium, we have 5 electrons from the nitrogen, 4 hydrogens, which is going to be a total of 4 electrons. And our 1 plus means that we subtract 1 electron. So NH4 plus would have 8 valence electrons also. Just to show you one example of using the charge there. Okay, so for the structure that we're working on building up, we've got our skeletal structure, we've got our 8 valence electrons. then we can start placing our electrons. So with those 8 valence electrons, we first need to connect everything. This is a molecule, everything's connected to each other, so we have to start by drawing in bonds just to get everything connected. Conveniently for us, we've got 4 bonds to connect everything together. 4 bonds is how many electrons? 8. So we've got 8 bonding electrons. So we've got no electrons remaining. So that's all that we would have to do for our structure for methane. If we had any left over, we would distribute those remaining electrons to our terminal atoms first, and then any leftovers to our central atom. We'll see examples of that. And the goal, again, is to get full octets. Then if we have placed all of our electrons, so if all electrons are placed and octets are still missing, then we form multiple bonds. So we can form double or triple bonds as necessary to get full octets. We will see examples of these. So the way that we would do that is we would move lone electron pairs from our terminal atoms, pop those in to be bonding pairs with our central atom. So we already saw the structure for H2O, but let's do it again, doing these steps. So our first step, we want the skeletal structure. We've got 2 hydrogens and 1 oxygen. Hydrogens have to be terminal atoms, so we're going to put those on the outside. That means oxygen is going to be on the inside. So this is our step 1. Step 2, count our valence electrons. So we've got 1 oxygen and 2 hydrogens. Each oxygen is going to have 6 electrons. Each hydrogen is going to have 1 electron. So that gives us a total of 8 electrons. And I'll usually call this VE because that's the nomenclature that's used on the worksheet. And then step 3, we want to place our electrons. So the first way that we're going to place our valence electrons is as bonds, just to get everything connected. So we put in 2 bonds to get the hydrogens connected to the oxygen. So that's a total of 4 bonding electrons that we've placed because of 2 bonds. So we've got 4 remaining electrons. The remaining electrons go where? With the oxygen. Our hydrogens have their full duet because of the 1 bond. So we're going to add our last 4 electrons onto oxygen. And then our step 4 would be double, triple bonds as necessary. Let's look at our octets. Hydrogen has 1 bond. So hydrogens have their duets. Oxygen has 1, 2 bonds plus 2 lone pairs. So 4 bonding electrons and 4 lone pair electrons. So it has a full octet. So we don't need any double or triple bonds in this case. Questions? All right, one more example. H2CO. Our first step, we want the skeletal structure. There's 2 reasonable skeletal structures that you might come up with. One of them is better than the other. So our hydrogens have to be on the ends. You might come up with this, HCOH, except we shouldn't have those bonds in there. However, there's a more symmetrical way that we can arrange this, and that's with oxygen on top. So this bottom configuration is a little bit more symmetrical. So that's the one that we're going to go with. We need to count out or sum up our valence electrons. We've got 1 carbon. That's got 4 electrons. We've got 1 oxygen, 6 electrons each, so 6 electrons. We've got 2 hydrogens, 1 electron each, for a total of 2 valence electrons for those. So our total is 12 valence electrons. Then we want to place our valence electrons. The first place that we put electrons is where? This is a molecule, so everything has to get connected. So the first place we're going to place electrons is bonds. So get our hydrogens connected to our carbon, get our carbon connected to our oxygen. So 3 bonds, that's 6 bonding electrons. And we've got 6 remaining electrons. We're going to place those from the outside, working our way in. Hydrogen already has its bond, so our hydrogens are happy already. So nothing to do with hydrogens. Our oxygen, on the other hand, only has 2 electrons. So it has room for 6 more electrons. So we can place the rest of our electrons on oxygen. And then our step 4 is fill octets with double or triple bonds. So our oxygen has how many electrons on it? 8. It's got 3 lone pairs and 1 bond. So each of these lone pairs is 2 electrons, and our bond, is 2 electrons. So oxygen has a full octet. Let's look at carbon. We haven't checked carbon yet. Carbon has 3 bonds, meaning it only has 6 electrons. So carbon doesn't have a full octet. The way that we can solve this problem is we can share some of oxygen's electrons. So if we put 2 of these electrons from oxygen in and make that a double bond, oxygen still has access to them. But now carbon does as well. And so we end up with this structure. in the bottom left corner, where oxygen has 2 lone pairs plus 2 bonds, total of 8 electrons. Carbon has 4 bonds, total of 8 electrons. So now all of our octets are filled. And that would be the correct Lewis structure. Questions? Okay, we'll pick up with more Lewis structure fun on Thursday.